Hello, guys. Welcome to today's topic. And today we are going to talk about scientific models. As we all know, models are something that are used to make representations of something. We use models, for example, architects use models to design what they want a specific building to look like. We are going to look at a few different kinds of models. So, when it comes to definition, models are literally representations of an object or a system, and they're normally used to explain how something works or to describe the structure of a given object. These can be patterns, these can be plans, these can be representations, or even descriptions that is designed to show the workings of a system, object, or a concept. In science, we specifically look at three different kinds of models. The first one is very simple, it's a physical model. It does not need any more explanation. It's literally what we normally do when we have a science project. We might create a model. A lot of y'all might have created or seen a model of a volcano. And again, the architecture experiment, sorry, not the experiment, the architects, the one that they make comes under the physical model. The second type that we have is mathematical models. Now, these kind of models are the ones that are made up of numbers, equations, or some form of data. Now, when you look down here, you will see the Punnett square. A lot of y'all might already know what this is, and if you have not, that's fine. We're gonna learn about it later this year. So how this basically works is it's a mathematical model. We follow certain procedures, certain steps, and we trace certain data and we find the results. So this is the example of a mathematical model. Now, the Punnett square is something that is used to study traits that are inherited or that is passed down from parents to children. And what we do is we try to predict the chances of a particular trait being passed down to the child. It can also be used to determine the gender or sex of the child that is yet to be born. However, it's obviously not very helpful, and we will discuss more about that later when we actually learn about the Punnett square. So yeah, mathematical model has numbers, equations, or other forms of data. The third type that we have is called the conceptual model. Now, this is the one where it's completely made up of ideas. So if there is a system of idea and there's a description that we need, it would be categorized under the conceptual model. Now, there is a lot of ideas out there. For example, the idea that the solar system is formed from a spinning disk of gas. This is a huge structure, a conceptual structure that can be categorized under conceptual models. Other example might also include the theory of evolution by Charles Darwin. This is a whole, there is so much research out there, and when you're trying to understand what it all is, you can literally pinpoint it and make a conceptual map or a model to figure out how it works. Next, we have benefits and limitations of scientific models. Of course, models are very useful, but not all the time. Now, some of the benefits obviously include that it can represent things that do not physically exist, or if they're abstract or difficult to track. For example, the theory of evolution. Now, it's an abstract idea, or it is difficult to track because human beings don't live for centuries to go on. But thankfully, we can use models, we can use scientific models to understand how it works, right? So this is a benefit. Or for example, dinosaurs. Dinosaurs don't really exist anymore, but we have models in museums all over the world to help us understand or visualize what they once looked like. Now, these can also represent things that are small, large, or complicated, right? So these are all the benefits. But again, there are also some things that can be added to the con list. Now, when you look under the limitations, you will see that they're extremely useful, but not always perfect. For example, especially if you're looking at abstract or non-existent things. Now, let's look back at the dinosaur example. Now, it's great that we have models, especially those that depict dinosaurs, because we have no way of actually seeing them, right? They're extinct. But again, if you think about it, if you think about the limitations of it, right, we have no way of knowing if they're actually up to scale. What if they just had big feet? Well, we know that's not the case. They are up to scale, but I was just giving you an example. But actually, an accurate example for this case would be if you wanted to know the strength that dinosaurs possessed, right, in their jaws. There is no way for us to find that out anymore, right? Now, scientists can obviously perform a lot of experiments. They can try using physics and chemistry to figure all of this out, but there is no way to actually confirm it because we have no real model to test the differences, right? So ultimately, such cases always end up being left out as a hypothesis, and we just don't end up having a result that is a definite answer. So this is a huge limitation that we must consider when it comes to scientific models. Now, next we have building scientific knowledge. Now, the world around us is ever changing, ever evolving, and it's fast. In 10 years, our world would be completely different than what we think it looks like now, right? There is no way to keep our world constant. There's technology and evolution, and it's just, it's going on and on. So, just like that, our scientific knowledge is also changing and it continues to grow. The more we conduct research, the more we learn about certain things, the more we realize, the more we add to our knowledge bank, and more we evolve, right? So, we need to move with the flow. We need to learn to adapt in the scientific world. And when we do more research, we can draw multiple or different conclusions from the same data. And a given data can show that our old conclusions that we already did or already had are completely wrong. So we need to learn to let go of old conclusions when needed and adapt and move on. We have scientific theories. Now we'll be looking at scientific theories and scientific laws. We have scientific theories here. For every hypothesis, more than one prediction can be made, right? For example, if I had a hypothesis that if I go to the dentist, my pain will go away, right? That's a hypothesis. Now that's one prediction, right? The pain will go away. But another prediction would be the pain would not go away, right? So every hypothesis has more than one prediction. And each time a prediction is proven to be true, the hypothesis continues to gain more support. Another reason why experiments should be performed numerous times, right? We want to make sure that we did not obtain a certain result by chance or by luck or other factors like these. We want to make sure that this is the same result that we will have no matter how many experiments we perform, right? And when scientists tie everything together about a given topic, like observations, facts, tested hypotheses, we finally form a theory. Now, theories are conceptual models. These can be used to explain various observations and also predict what might happen in the future. For example, the theory of evolution by Charles Darwin. Now, this tells us what might happen in the future, how we might eventually adapt to function better in a future world, stuff like that. And contrasting this, we have scientific laws. Now, scientific laws are the ones that summarize numerous experimental results and observations. And it basically explains how things work, what to do in a given situation. Now, the only difference between laws and theories is that, unlike theories, laws do not predict what might happen in the future. Instead, Laws are statements of what will most definitely happen in a specific situation. For example, Newton's law of motion. Now, this is telling you that no matter what you do, the only end result you will find is ABC. That's what laws are telling you. But on the other hand, theories might tell you, oh, this could happen, this might happen, but they're not giving you 100% certainty. So that's the only difference between theories and laws. Now, for example, when we have the gravitational law, it is a law because no matter what, if you throw something, it will always fall towards the center of the earth. That is a law. It's not going to change, right? So yeah, that is law. And this is the independent practice that you have for today. You just have to watch a video and complete the lab assignment given to you guys. I hope you guys have a great day. Again, please go ahead and ask me questions whenever you have any. I'm here to help you guys. Also attend the Zoom live sessions, and if you have any doubts, we'll clear it then. Have a great day, guys. I will see you later. Bye.